Good morning, everyone. Welcome to our ESI webinar. Today we'll be discussing the VA1 2018 release. The webinar will be presented to you by Chad Musser. If you have any questions, please raise your hands or use your chat box, and we'll have a short Q&A session at the end of the presentation if time allows. Thank you.
Excellent, thanks Saskia. So here we go. This is the second of today. There was an earlier one more for people in Europe or for on the East Coast. And welcome, here we go for our usual walk through the new release. This is intended to give you a good flavor overview of the main new flagship features here in VA1 2018, which was released, published to my ESI, and made available a couple of weeks ago. So here's the outline of what we'll be discussing today. We have quite a few new topics, a little bit more packed release than usual. And most of the new functionality revolves around an upgraded and enhanced ray tracing solver that we've specialized for our purposes, fitting in really well, slotting in to link our existing boundary element and SEA statistical energy analysis solutions. So you'll see most of this hour dedicated to discussing these two linked topics. The first with ray tracing is a full independent steady state solver. You'll see how that fits in with the existing methods. And then secondly, how that improved ray tracing also improves the speech clarity tool, which we've had before. This is something more and more important, useful for supporting, for example, speech intelligibility predictions for voice recognition systems, hand-free, dealing with interior noise, and basically being able to make sure that voice commands and understanding comprehension is going to be achievable, mostly for interior vehicle design. Good, we've got a couple new enhancements to ray tracing that will support speech clarity, allowing multiple sources, allowing directivity, but you'll see a lot of similarities between that and the steady state ray tracing solver, and we'll handle discussion of both of those at once in the main part of the hour. The next topic is something called a DFAT, or Direct Field Acoustic Test Module. This is something a little bit specific for aerospace and launch vehicle industry. This is a virtual test or a simulation in support of a new wave of testing being done with stacks of speakers rather than the old traditional reverberation room. Mostly trying to show they really want to establish that this type of test gives you an equivalent sound field, properly diffuse. We can use simulation, virtual testing to characterize the field and show that it's diffuse or show what kind of field you have. This is interesting not just for launch vehicle and aerospace people, but to show how we can work with fully and partially correlated loads and try to optimize test setups or show the character of the acoustic field that you're dealing with. That's key, not just for launch vehicles and a specific structural qualification, but for acoustics and vibration problems in general. We have some interesting new enhancements related to trim modeling, sound package treatments, multiple layers. So we finish off what we began in 2017, offering some lighter, cheaper, faster, more flexible options for trim modeling. Not as accurate as the full finite element poroelastic representation, but achievable for a lot less cost for modeling and running, calculation time. So we show what those are, how they fit in our portfolio. We have a lot of ongoing performance and efficiency improvements, some low-hanging fruit, as it were. And this is not specifically 18. This was released in 17.1. But we have a new available grid tool for parallelization. This is a nice way of interacting, of setting up and breaking down models that might take a longer time into batches by frequency, different grid jobs. And we've got that tool now to support not just boundary element. We had a version in the past. This is a much more elegant way of doing things, less file transfers, more automated, more robust, and it now supports not just boundary element, but most of the solutions across the board. So we'll touch on that. So if I collapse that outline down, we'll go through item by item. I should point out we're happy to have questions, comments, discussions and clarifications. In this format with multiple attendees, it's usually easier to wait till the end. So if you don't mind holding them, I promise to leave at least 5 or 10 minutes at the end of the hour where you can raise your virtual hand or type in a question to the chat box or even ask to be unmuted and represent and ask your question. So this is what we'll step through, and I do have one extra topic to touch on. We have introduced with this version flexible tokens, and those are now commercially supported as well. I'll mention briefly what this is. This is in keeping with the rest of ESI that's had tokens for a while. We now have specific tokens for vibroacoustics. As of today, they're released only available for the vibroacoustics projects and products, but we may try to link those in the future. I'll give a brief overview. That's something to discuss commercially with your local representative, and it may be attractive because it really opens and unlocks the full range of solver and module options. So let's start with ray tracing and the related speech clarity. So the concept is fairly straightforward, fairly easy, some basic physics. We do have as our basic fundamental underlying source for ray tracing a compact acoustic source. So this is a little bit of an expansion evolution from our previous monopoles. This is something that a monopole is a type of compact acoustic source, but more generally, a compact acoustic source has directivity. So in the different angles and direction of propagation, some angles might be stronger or weaker than others. One of the classic examples is to just look at a dipole instead of a monopole. And you can achieve a dipole by having two correlated monopoles. This is another way of looking and saying, hey, this is a simpler way to represent complex sources. Instead of a collection of correlated monopoles, a single compact source, usually spherical, not an absolute requirement. We can work with other shapes, but this is a nice flexible source, elegant. You can just describe as a single source, something with a very complex directivity, and other than being in the very, very near field, it's a good and accurate representation. So we introduce and make this the fundamental source for ray tracing. Remember, we assume that the source is a spherical wave, certainly for the spherical sources, or at least a directive wave from a compact single point center. That's the definition of the compact acoustic source. So what do? We simply discretize the source by angle into different rays. We really generate quite a few of these. Pretty normal and common for us to generate and shoot out up to millions of rays. You'll see we have a very efficient engine for doing this and processing this. So it's a good brute force, easy to understand technique. Sends out thousands, hundreds of thousands, even millions of rays, tracks the reflections, tracks the losses at the boundary, tracks the angles of propagation, and adds everything up all at the end at one or more receivers, including all the phase effects. So it can run in a deterministic way. We are obeying geometric reflection laws with a couple of advanced, or you could say more specific enhancements that fit in well with our solutions. Options. For any surface, you can pick to have a sort of smooth reflection. The angle in is the same as the reflected angle out. Following Snell's law, kind of a deterministic, very literal interpretation. And we have a second option, which you don't see so much, but this fits in really well with SEA, some of our coarser approximations, or even some of the higher frequencies, which do tend to be a rougher surface. As the wavelength gets smaller, it sees roughness and scattering that the low frequency long waves don't necessarily see. So we already have two options that I'll come back and discuss later, but it's enough to know that for the rough one, you have more scattering, and the main energy comes out at an angle that doesn't have to be identical as the incident angle. We have a distribution function at which that ray can propagate, and it's likely to come out close to the incident angle, but doesn't always come out. It can be modified plus or minus a couple of degrees, and you get some statistics in. That fits well if you have a coarse or more approximate geometry where a literal interpretation doesn't really make sense for that kind of model. So we have those two options, and the other thing we have when we talk about geometrical reflection, we have a really good way of modeling treatments, trims, noise control multiple layer of fiber, foam, mass barrier, air gaps. So those also take into account the incidence angle of the sound wave in terms of how it absorbs and reflects. We do model full details of the trim, multiple layers, complex impedances. So that's much more advanced than a regular ray tracing code, which might only model absorption as a function of frequency. We're modeling complex impedances or multiple layers, if you like, and taking into account the effective angle. That keeps with modeling the full details of sound package treatments and trims. So how's this implemented in general? Well, we're just using an image and source method. So for each source that we're calculating and each receiver that we're looking to get a response for, and remember, this isn't the limitation. This is just source by source, receiver by receiver, how we're calculating. But it's very normal to have multiple sources and almost always the case that you have multiple receivers. They can be points, individual sensors. They can also be data recovery surfaces, entire faces, and that's a nice advantage versus real physical test. You'll see in a little bit, if we use a face, we can have a lot of detailed, fine, accurate information about the character of an acoustic field, which is hard to get from test. So this is the basic way that we're simulating and coming up with a problem. You've got a source with a direct line path. You can generate source images corresponding to the reflected surfaces. They have a reduction of magnitude and a change of phase according to what's on the surface. And you're adding those up with all their relative phases and getting a total answer, both for the steady state solver and for the speech clarity, the transient version. We should mention that the general formulation for speech clarity hasn't changed from previous versions of the tool. We're using a transient version of ray tracing to get the direct sound, that first direct path from source to receiver. There's only one. Then you have some early reflections off of the first bounces, the first faces. You start to lose a little bit of energy, but not too much. And then finally, you have late reverberation. You have energy that's reflected a couple of times, had a lot of losses, and you get into a lower steady state kind of reverberant regime. And we continue to use SEA to calculate this background noise for interior spaces, form a sort of limit in time for your reverberant background noise. And at that point, you don't need to track individual rays. It becomes a lot more statistical. So we're using ray tracing, doing our bookkeeping, record keeping for direct and early reflections, SEA for late reverberation for the speech clarity, and those ratios give you your speech intelligibility or your key psychoacoustic metrics or decay metrics. And those are used to determine how clear or intelligible speech and decay times are within a cavity. That's important for vehicles, for understanding if PA systems are going to work, infotainment systems, if you're going to have good hands-free and voice recognition awareness in a vehicle or not. So you'll see a lot of commonality. Again, setting this up, it's only that last step of realizing if you wanted to do a steady state ray tracing for transfer functions, or the transient version to get speech intelligibility or room acoustic indices. That's kind of the last step. Up until then, you have a lot of common parameters. You're creating geometry from FE faces, SEA subsystems, pretty robust, doesn't rely much on meshes or a lot of details. It's lightweight, kind of fits in with the SEA concept. You're specifying materials, so you can put absorptions or impedances or actual multi-layer treatments on the faces, specify if it's smooth or rough, specify if you have some losses from diffusion on a rough surface. Putting in the sources, always very important. And remember too, we do have directive compact acoustic sources, so you need to properly orient and specify the source strength versus frequency and also versus angle. Finally, one or more receivers. These can be individual points. These can be large faces, where they are, and also the size of a face or the radius of a receiver. We're doing some work to automate and provide some user recommendations as you go to model what's an ideally sized sensor. But for now, we've got full flexibility, how large it is and how many rays it catches that add up. So we've got some graphical algorithms. We're identifying the reflecting surfaces, setting things up as I showed before with the images and sources, and we're piggybacking. There's a lot of improvement in the last 5 or 10 years for ray tracing in support of graphics, in support of some real-time virtual reality type of applications. So there's a lot of kernels that we could piggyback to track and keep track and use to have a very performant, very efficient engine to just cast rays, post-process, and generate and do the bookkeeping for ray tracing. So we set the ray paths, shoot them off. Again, for steady state, you're just collecting the sum of all the different paths at the different receivers, keeping track of the magnitude and phase. Those are your transfer functions or frequency response functions. If you're doing speech clarity, then you're getting an impulse response and using the ratio of direct and reflected sound to get speech intelligibility and other key indices. So the applications are really unlimited, but these are some of the more normal ones. Interior noise. The original speech clarity was intended for train cabins, aircraft cabins, things with PA systems. Larger, where you expect maybe not an equal response. It's a large cabin, a lot of absorption. Some points in the cabin have louder or softer responses, different ratios of direct and reflected sound. But we see more and more for cars, smaller vehicles, things with infotainment systems, voice recognition, hands-free. You have some variation. You'd like to break it down into direct versus reflected as well, and it's a useful tool for that. We know the speech transmissibility for vehicles or for other buildings, room acoustics is a key application. And we really take advantage of the new steady state solver for exterior noise. This really opens us up to being able to do some vehicle or general exterior noise predictions, calculations. And again, I mentioned this really unlocks capability. Boundary element can, of course, do these predictions, but at a very high computational cost for high frequencies and large models, large numbers of nodes, challenging in time and in CPU in terms of memory needed. Ray tracing fits right in. You can take a component level analysis of a source and how it's propagating from boundary element and expand that up to a very large model environment level, full frequency and ray tracing. And that's a nice combination for exterior. And we have a way to link that in to panels if you want to go ahead and do an exterior noise based off of that. So I can remind you then what we have and what today are the relative advantages and disadvantages. In other words, how does ray tracing fit in with our current BEM and SEA methods for modeling acoustics? So remember, boundary element is still, overall, at the end of the day, the most accurate solution. It's available as a coupled solution with fluid and structure. It includes diffraction effects. It's the full, most accurate answer. There's no real frequency limitation. It just gets difficult as you go up in frequency and the model dimension. You start to challenge the amount of memory and computation time you need. So ray tracing is a nice alternative. We can and do use boundary element or test to define the compact acoustic source, the directive source. And no problem in terms of modeling complex geometries. You do have some steps to be taken to make sure that the model, the geometry is modeled in a way that's friendly and meshed properly for your BEM model. But the geometry itself can be very complex. We do have another limitation. We don't really have the same scattering models for rough surfaces, the statistical things we've introduced to ray tracing. So if you have a coarse model or expect a lot of scattering, that's a disadvantage of BEM, but otherwise the only real disadvantage, which is a big one, is the amount of modeling effort needed, the time and the memory resource. But I do mention and remind you, with the new grid capability, the performance improvements, that's less and less of a concern. It's more of a trade-off. What stage of the design, how accurate do you need, and do you want to run some faster, quicker loops with ray tracing or a concept phase loop? On the SEA side, you've got a lot of advantages, but again, this is a very different physics from BEM or ray tracing. So SEA can be faster than BEM. Good for high frequencies. We still use SEA for the background noise, the late reflections, the reverberant noise for speech clarity. But remember, this isn't following the same physics for propagation as ray tracing or BEM. We're using average properties, so we don't have individual point responses. We don't have individual sections of a cavity being shown to be louder or softer or any phase effects. And here's the big one. SEA is pretty good for interior noise problems, but it has a steady state reverberant diffuse field assumption. That's really key to the whole method, and you don't have that externally. So for external problems, you can really forget SEA, look to BEM, ray tracing. Finally come back, have a good look at ray tracing. No real maximum frequency limit. It can get very rough at high enough frequency, but usually above audible frequency. Nice and quick. We do have direct and reflected field contributions. We have this new directive compact acoustic source. It's compatible with SEA through a general surface pressure. And this is really nice and valuable. I can mention this later, but essentially we can bring this in to act as a chain between a very detailed source characterization with boundary element at a component level, propagation, especially in the exterior with ray tracing, and we can collect the response, the pressures on surfaces, use some of this new general surface pressure capability to make that an SEA load. So it's a great way to chain a detailed BEM or test source characterization, propagate, especially through exterior in frequency range and model size that's challenging for BEM, and excite SEA models at the end. Remember too, this is truly our first time domain solution. We end up getting frequency response functions in steady state mode, but we are calculating and can calculate in time domain. We take advantage of that explicitly for the speech clarity. What are we missing today? Well, again, we don't have this fluid structure coupling like we do for boundary element. So for coupled structures, this basically means if you expect the acoustics to excite the structures and interact and have some two-way interaction, then you still need BEM at this stage. There are some interesting things we're exploring to see if we can change that in the future, or at least work with pure SEA models and allow the transmission through the structures. But still a little bit in investigation, which means right now better for the pure acoustics problem. And the other one is today, with this 2018 release, we don't explicitly have diffraction. We have some clever phase merging algorithms that make that a little bit less pressing. But for exterior problems, if you're in a shadow region, sort of where the sound is propagating around the corner from a source, then BEM is still needed for diffraction as we work to make diffraction in 2019 VA1 for ray tracing one of the key features. For interior problems, we usually don't need it. For exterior problems, if you have a straight line of sight, source to receiver, or just some reflections, it's second order. But to be complete, we do need and are looking to implement some of the, you could say, more established recent ray tracing diffraction models into our solver for the 2019 release. So I can sum it up as following. What do we have that's new? Okay, well, the whole steady state analysis is new. We can do multiple sources. We can specify directivity from BEM with our own calculation or from test or other simulation. We can handle arbitrarily shaped obstacles and complex geometry. This one's key. We can do all of our detailed trim analysis, multi noise control treatments, different layers. We can also use complex impedance, not just an absorption coefficient. We can account for diffusion as a loss effect, and we have different reflection models for different roughness and diffusion. One's a little better keeping with an SEA model. One is more deterministic if the geometry is fine and detailed and the surfaces are fairly smooth, or if you're comparing to an existing deterministic model. Speech clarity is an enhancement of the previous tool. Again, you can have multiple sources with directivity now. We can account for background noise through SEA. Same thing for noise control treatments. And we can predict speech transmissibility index, the rapid version, the regular version, decay rates, ratios of direct and reflected sound. We can validate loudspeaker placement. We can show if infotainment systems or people talking will be properly heard in a car or a vehicle of any sort, and show how changes to speaker placement or sound package trim can change, improve, meet the target. So again, we have sources with directivity. We can calculate these parameters now. We've done some speed with the new kernel, new strategies, robustness of the geometry, and some overall fixes from the last versions of speech clarity in VA1. This is what it looks like in practice. Here are the forms. You define sources. You have pressure, magnitude, and phase for when you're using steady state mode. You have ratios of amplitude for speech clarity because that's an impulse response, so you don't have a frequency dependent spectrum. You can store them here similarly, and the information that's used depends if you run the steady state solver or the speech clarity mode. On the faces, you have a lot of options. You can specify it's reflecting or a data recovery face, and then for both sides, you have options to do diffusion coefficient, that's a loss factor. If you have a multiple layer noise control treatment, which you've defined in another part, which you could be using for your SEA or other model. You've got noise control treatments. This is specifying, this is showing if you want to have an impedance applied, which can be complex, as I mentioned. And then finally, front and back surface, are they smooth and deterministic or rough with some scattering and some variation of reflection angle? We have a couple validation cases that we've run. We've been looking at this now for most of the last 2 years. We've done a lot of cases, simple and advanced, and here are some good comparisons versus boundary element, showing up to high frequency for a lot less calculation time. You can recover a couple sensors, 4 sources, 4 sensors. At 2 of the sensors, pretty good throughout the frequency range. Not quite the same dropout at a couple frequencies, and the lowest of frequencies, where you may have some diffraction effects or near field effects, not identical, but otherwise pretty comparable, giving you confidence you can use ray tracing instead of boundary element for a lot of problems. So here is showing use of the directivity from the boundary element calculation or the common loudspeaker format file. Again, you've got the magnitude and phase of a pressure spectrum or the relative amplitude for speech clarity. You're positioning with a location. You're showing if it's a monopole or directive, and then offsetting, so you're placing the location and rotating it to the proper orientation. You can pick a frequency, look at its directivity pattern, and again, you can see you're either using it for a steady state mode, getting a frequency response function comparable to boundary element, or speech clarity, speech intelligibility, those types of metrics. So we didn't reinvent. There's an existing standard common loudspeaker format that's used for speaker or point source directivity. You can view it in 3D, you can view it in a 2D plot. This is a third-party, freely available reader, CLF reader, available from this site. And a lot of loudspeaker manufacturers will provide this. You can also use that format for your own test data or a simulation outside of VA1 if you want to bring that in. And you can see and view in full detail the source directivity characteristics. So again, we've done this for a lot of interior and exterior problems, interior things like mufflers, exterior things like pass-by noise, and gotten pretty good comparison through the frequency range to boundary element, the existing acoustic methods. We've published some of these in recent conferences, Internoise, for example, last year, this year. And here's a good example of the chain using a component level boundary element model to get in the relative near field, not the official near field, because a compact acoustic source isn't a good near field representation. You need to be at least a couple wavelengths out, but to have a smaller physical model capture the directivity of a radiated structure with BEM and be able to use that defined compact acoustic source in the ray tracing larger model up to high frequencies. That worked pretty well. This was a trained pass-by case being pushed up to 6,000 or 7,000 hertz. Good agreement with a boundary element reference calculation, showing you can use ray tracing faster and easier for this type of application without too much loss of accuracy. Another interesting use is a large cavity. You can think of this as a cabin, passenger cabin for aircraft or train, for example. So we've got the ability here to do show from a directive source the distribution of energy at different locations in there, hot spots, cold spots, areas where you have more direct sound than reflected sound, for example, that sort of thing. That's useful for design. And to wrap up showing you how this is chained, again, you can use boundary element. You can do exterior models, for example, working with a pure SEA model, an exterior ray tracing model, capture how the exterior sound propagates. This example showing tire noise, how you get the greenhouse panel acoustic response on the glasses on the other surfaces. And then we can take advantage of some capability we introduced for wind noise and aerovibroacoustics. We can do a wave number frequency spectrum analysis, convert these surface pressures into acoustic loading, and apply those directly to your SEA model with the general surface pressure, get the resonant, non-resonant paths. This is really big. We've always had the ability to use boundary element to get the greenhouse panel loads, but that conversion was always tricky. You had to set up a boundary element model. It could be challenging in terms of computation to run, and then you had to sort of fit that or explore how to turn those into equivalent acoustic loads in SEA. Not anymore. You can have the full complex correlated load applied to SEA as a general surface pressure, and you can sort of see we have a chain where boundary element component models feed large ray tracing models that can go to high frequencies, large models, fast, little effort, and you can then transform those through wave number analysis into general surface pressures, all within VA1, step, to the point where you can get your SEA vibration or interior acoustic responses pretty easily. And speech clarity, just to remind you the kind of problems we're doing. Yes, we're trying to get decay rates. D50 and TS are ratios of direct versus reflected sound. That lets you know more or less how things are going to be perceived and heard, clearly or not. And then STI and RA STI are metrics to indicate how clear a person will perceive sound, important for hands-free, voice recognition, PA systems. So as I told you, that's the heart of the new features, the flagship features, ray tracing and how that supports speech clarity. We have a new direct field acoustic test module, specific for launch vehicles, but bear with me, the concepts are pretty useful overall for a lot of acoustics. What we're trying to do here, as I mentioned, is as people are going to the speaker stack test to replace a big reverberant room to qualify and blast structures of sound, show that it's going to vibrate within tolerances and not break. Well, they're using more and more this speaker test. It's cheaper, it's easier. You bring it to the hardware instead of transporting hardware. You can set up and do this very quickly. So what they're trying to understand is make sure that they understand the characteristic of the sound field. They want it to be nice and diffuse and reverberant, like the reverberant chamber, so that they know it's an apples to apples testing. So through a lot of experience working with our main partner, Maryland Sound International, they're the main test provider for the service with the equipment. We've discovered that we can model those speaker faces as boundary element surfaces with a velocity constraint and with relative correlation to each other. You can then predict virtually the response of a coupled structure, as well as some point microphones or data recovery faces near the structure where you want to try to prove the sound field is reverberant and diffuse. So everything you do in the real test, you can do virtually. And because the real test has a couple discrete microphones as points, you can't really fully prove the character of the field. It's only with our way of modeling with the virtual test, the simulation, the data recovery surfaces, you can have as fine resolution as you need spatially to show if it's truly diffuse, if it's truly reverberant. You know what a truly diffuse and reverberant wave number transform looks like from the theory. So a diffuse acoustic field looks like a ring, looks like a circle if you look at one slice of frequency in the spatial direction or the wave number space direction, X and Y. And you want to try to run your simulation and calculation and see for some representative recovery surfaces, does it look diffuse? So one of the points of our thought study here is to show that the vertical direction because all the stacks are in the horizontal direction here, you can see these are all perpendicular to the ground, all the different correlated speaker faces. So we can already show in the plane that's parallel to the ground, it doesn't look very diffuse. It doesn't have the character of a diffuse field. You can see that by looking at this plot, and you can see that by looking at the wave number frequency transform on the right in a plane that's also perpendicular to the ground. It does look diffuse. You see the ring at the different frequencies. A couple hot spots, a couple relatively colder spots, but it looks like a ring. That means it's diffuse. That means it looks like and is equivalent to a reverberant test chamber. On the left, that's perpendicular to the ground. You see it only looks like a ring in one direction. It isn't diffuse. You need to change your speaker correlation, rerun it, or explore changing the geometry and angles of some of those faces if you want to get it diffuse. And the other thing you look for is hot spots and cold spots. A hot spot means you have extra acoustic energy at this angle of propagation, and a colder, darker spot means you have less acoustic energy. Then you need to be worried that you're not properly exciting and testing the structure and the structural modes in response enough to qualify and prove it's going to survive a regular operating condition. This module's got an easy walkthrough way of generating those speaker faces. It's a very repeatable system. You have a slight modification in speaker setup, position, location, correlation on a case-by-case basis, depending on what you're testing. But no matter what you're doing, you're setting up these common speaker faces just like this, and the tool will generate them quickly and easily, get your BEM model up and ready to run in just a couple clicks. That's really helpful. And same thing for defining the sources and getting this set up. Once you have that nice and quick and easy, you can tweak it if you like within the regular VA1 environment. So we do have, again, the tools I was telling you about. You can look at the wave number frequency spectrum, again, looking for hot spots and cold spots. You can't do this with real physical test. You don't have enough spatial resolution with your couple discrete points. So the simulation and virtual test can show you the diffusivity and hot spots and cold spots in a way that you can't test yourself. That's really helpful. So again, very specific for launch vehicle, but this is something more and more we're doing for virtual test, characterize sound fields, help to understand or even design correlated sources throughout the industry, not just aerospace. Good, so we have some interesting new trim modeling tools. And if I back up and talk about a little bit of our portfolio, again, we're looking for different options. In the same way we offer ray tracing as something lighter and faster and easier, as opposed to boundary element, which is more accurate but takes more time to set up and more time to run. Same thing for trim. A lot of our customers and applications throughout the industries are trying to design and optimize trim sound package treatments, and we've got the tools to do that. In SEA, we're usually using a transmission matrix method to do multi-layered treatments. Nice, simple, lightweight, works really well for SEA. The locally reacting assumption is fine for that. And until this last year or two, we've had a much more detailed representation with poroelastic materials that's been more appropriate on the FE or deterministic low frequency side, or for some of the deterministic parts of hybrid model. We know it's very accurate. It's fully accurate, fully detailed, all the interaction, but takes some time to mesh and set it up and take some modeling time, both to set up and to run. In fact, running it can take more time than the actual underlying structure of the vehicle. So we've balanced and mixed in a couple new ways to model trim. In the last release, 17, we introduced this 2x2 area isolator, where with a meshless way of specifying trim, very similar to doing the SEA type trim modeling, we've got a way, an improved way to get more or less automated way of calculating and putting that into a coupling that trim effect. And because this is this can be much more approximate than poroelastic material, we've introduced in 2018 a middle ground. A non-locally reacting model, it's also meshless, similar setup to the locally reacting model, but accounts for some interaction, more interaction, at the cost of just a couple more minutes or at most an hour of modeling. Is a lot more accurate than locally reacting and a lot easier to set up and calculate than the poroelastic material. These are the kinds of configurations we're talking about. Multiple layers, foams, fibers, porous materials, septums, mass barriers, air gaps, etc. So if you've used 2017, you've seen a couple options for specifying the treatment. We've got a nice interesting way with some flat and locally reacting assumptions to do some smart angle averaging and using a transmission matrix method to generate a 2x2 area impedance that we can use as a nice simplified trim modeling mechanism. And as you'll see in a validation case, if heavy barriers aren't involved, it can actually be a very, very good, pretty accurate representation. Here's what's new for 2018. Again, for something that's relatively flat and laterally unbounded, you start to take into account some two-dimensional interaction effects, non-locally reacting, some point-to-point interaction, and that necessarily gives you some more accuracy for the same sort of setup and just a little bit more computation effort, but a lot less than poroelastic materials. So here's how the portfolio lines up. Most accurate and complex is still poroelastic material, most accurate, but a lot of meshing work and a lot of computation time. The 2x2 locally reacting doesn't require meshing. It's really fast, essentially costless as a developer. I can agree with that. But in some cases, especially if you have heavy barriers, you know you're trading off accuracy for that setup and run benefit. So now sitting here in the middle, you've got analytic transfer functions, again, no meshing, but you've got some more accurate and less expensive by orders of magnitude than poroelastic materials, more accurate than the area isolator. So again, depending on what you need, what stage of the design, you've got a couple different options now for modeling trim, and it's flexible depending what you need, how much time you have, etc. So we have a case study, a validation example with a carpet, different sections, different layers, different trim configurations. The red curve is that new noise control treatment, the non-locally reacting. The blue one is the locally reacting, the 2x2, and the dash green is poroelastic material. You see, with a couple small exceptions, most at low frequency, very similar response. In this particular case, this built some confidence. We'd like to have an example with heavy barriers where we can show the locally reacting breaking down a little bit. Always good to understand and know limitations of a method. But we know from these studies and some other work that we're doing that the two new options, which are much simpler and easier, can offer enough accuracy to be of interest, especially for optimization loops or early phase designs. This is for velocity response on the panel. On the look at radiated noise to the interior. Again, pretty similar, certainly enough for design work. These are 4 different sections. The 3 methods compare very favorably. So let me just talk briefly about a couple of the main performance improvements. We do have a faster GUI refresh for large models. For some of the larger models too, we have an improvement and increase you'll see mostly for large models, tweaks, optimizations, maybe about a 10% time increase. And what I mentioned at the beginning, we now have this regular grid parallelization tool, nice and robust. You don't need to, this isn't an add-on. If you have enough licenses to run this, then it's simply available. You can piggyback and use grid parallelization for things that take a longer time. You break it into different grid jobs. Those are batches of frequencies. So for example, you might break things into 4 batches of frequencies, each solves independently, and the grid tool will merge the results at the end. You don't even need to worry about transferring files from the machine that's calling the original solve from the beginning like you did in the old grid. So that's an improvement. You can mix and match and use different solvers, some of which might take some time for a large model. And you've got different grid jobs for these methods. You usually have especially under tokens, certainly enough licenses to be able to support that. And that brings me to the last topic, a brief mention of the flexible tokens. What are they? So I think most people in the industry, or even those using other ESI products, know what tokens are. They're flexible. They're giving you flexible access to the different range of solvers, modules, different capabilities. So 2018, a VA1 has it. It's available as an option, supported already, I believe, even in December. Commercially, you can talk to your local representative, and you have a common token pool unlocking access to all the solvers, including the new ray tracing solver. All of the modules, including the enhanced speech clarity, the DFAT modules we just discussed. The only thing outside those systems are the user interface, which you can now purchase extra for the first time if you need them. If you have a big token pool and you want to support multiple extra users using them, you can add on GUIs. It's just not part of the token pool. And third-party products, things that require royalties like Nova and Fomex from Mecanum, that we are the exclusive distributors for, or some of the CAD importers, well, that's outside of tokens. Necessarily, we can't include those for royalty and legal reasons. But everything else is on the table, very flexible. You'll also see that the tokens are competitively priced for the grid approach, for parallel model building and solves. And of course, everybody right now is a non-tokens user, and everyone will get the chance to step forward and migrate to tokens if they wish. You can't have half and half, so you need to make a decision, but tokens are really flexible, powerful, and many users already have expressed interest or commitment in migrating and taking advantage of these benefits. Before the Q&A, I want to give you a little teaser and preview. Of course, we're already working on VA1 2019, as well as the flavor VPS, the NVH. That's the main FE solver at ESI, and one we're increasingly using. So I can remind you, putting diffraction into ray tracing and completing the exterior full range solution is very key, important for us. That's one of our most important things for the 2019 release, which should be in fall of 19. Getting that compact acoustic source that's been so valuable for ray tracing, flexible and available as well in boundary element. So the user can have the same load and say, well, let's try it in ray tracing. Oh, I have more time now, let's try it in BEM. That's valuable, we're working on that. I didn't talk much about the pass by noise tool. It kind of has its own life as a separate product, but we're working to improve that, let it support correlated sources, and get some of the ray tracing and faster calculation methods in there as options. The DFAT, this is our first version, our first release, and we already have some suggestions and tweaks for optimizing sources and other things that we're introducing. And we're starting a multi-year plan to do a nice big enhancement set of upgrades on the user interface. We're looking to improve the geometry engine to make it more supportive of usability, especially for SEA, for ray tracing, for trim modeling. Things that don't need heavy meshing and nodal requirements. So we're working on things that are going to offer more automation, enhancements, ease of use, as well as let users customize and script on that basis. So stay tuned. 2019 will be the first step forward to really sort of modernize and make this more accessible and usable across the industries and user base, especially for SEA, SEA framework, ray tracing, and trim modeling. On the VPS NVH side, we are committed for 2019 to switching to VPS, our very powerful ESI in-house FE code, as our periodic and FE solver. That'll have some immediate performance benefits for us, as well as the range of problems and element types we can solve. And we'll also leverage that with the upcoming direct frequency response for pore elastic material capability. We'll plug that right in and take full advantage of that in our pore elastic material hybrid solves. So that's the main functionality coming up. Pretty excited, already working on this, and should be in beta mode already in about 6 months' time, with a release in about 9 or 10 months' time, according to plan. So that's 19 coming up. And at this point, I've more or less finished the overview. So I would throw open the floor, see if somebody wants to type a question in, raise their virtual hand, or ask to be unmuted with any questions about the functionality we've discussed, or any of the upcoming plans. So thanks for your kind attention during this hour, kind of a fire hose, a lot of concentrated information. Um, Perfectly appropriate at this time to type in a question, ask a question, and I can note too, this recording will be made available at a later date. If you'd like to review this again with the material, this exact recording I gave, or share with a colleague in-house, we do ask that you don't distribute outside of your company, but again, that's available. Thanks for your time and attention, and let's use these last minutes for a Q&A if there are any questions.
Thank you, Chad. Please don't hesitate to raise your hands if you'd like to ask a question. And as Chad mentioned, the recording will be available by probably tomorrow at the latest. And if you have questions that come up in the next few days, please contact your representatives. All right.
Okay, good. Well, and you can also contact us as well. I know it's a lot of concentrated information. You can always contact us or your local support for any demonstrations, information about these features. So thanks for sharing this hour with us. I hope it's been helpful and beneficial. Saskia, thanks for the support and help.
Thank you.
Any last words for the audience, or we'll let them enjoy their day?
Have a great day.
Okay. Thanks, everyone.
Thank you.
So long.
Bye.